Orthographic drawing lecture 2. So today we're doing the number of views first. Orthographic drawings are drawings of 3D components, but it's multiple 2D views from different angles of the 3D component. Generally we require 3 views or even more views of an object to fully describe the shape of the object. But the number of views depends on the complexity of the object. If we consider this component, you'll notice it has an axis through the middle and everything is kind of symmetric spaced around it. So this object would be termed a cylindrical object. Cylindrical objects typically require only 2 views to fully describe them. You'll notice any of these holes, that groove, the hole through the middle, those sizes there, all of that can be described by simply using these 2 views. Other components like a flat plate, or if you consider a paper cut in a certain shape, a component with uniform thickness, flat component, most of the time we can actually get away with only 1 view with a note that states the thickness in the 3rd direction. The number of views required to fully describe a component, as I mentioned, depends heavily on the complexity of the object. Please go and watch this video that explains, even with this very simple component, how we need at least 3 views to fully describe it. Next we've got the line alphabet. We have mentioned this before in the course, but today we're continuing with 2 of these extra line types. Well, 3. The continuous thick one is used for outside edges or visible edges of components. Continuous thin one we'll use later on for dimension lines. In today's class we're going to use it for hatching. You can use it for imaginary lines of intersection or leader lines later when we do part numbers. The dashed thin line is used to show hidden detail, basically information of a feature of a component that lies behind another feature. For example, a hole that goes through the center of a component. The chain line, long, short, long, short, long, short, is used for center lines and symmetry planes. Continuous thin freehand is used for break lines or limits of partial views. And the chain line thick at the ends is for cutting planes or of sectional views. So center lines. Center lines are used to show the axis of a cylindrical object. Now the advantage of showing a center line in this view, if I only had this rectangular view, having the center line through the middle actually already indicates that this is a circular component. Or at least something in this component is circular about that axis. It can also be used to show an axis of symmetry. For example, if we go vertically, the right and left look the same, top and bottom look the same around the horizontal line. So center lines on cylindrical features will always show one in the axis of the cylinder. It extends past the end of the cylinder by about 5 to 8 millimeters. And we also show the center lines in the plane of the circle. So where you can see the circular feature, we show a vertical and a horizontal one. We actually do this on isometric views as well, for the plane of the cylinder, not for the axial direction in isometric views. Hidden detail is used to show what's going on the inside of a component. Now for clarity, it is often necessary to show edges that are not visible to the observer from the outside. This is shown using dashed lines. It should be omitted unless it is needed for clarity. So if I don't know what's going on there, I need to show it with these dashed thin lines. The dashed lines are approximately 4 mm long with a 1 mm gap. They should be in contact with the outside lines where they start and end. This is important so that we can see that the hole starts on the outside surface and it isn't something that stops very close to the outside. This feature over here, it's basically two circular holes with the material in between removed. That is called a slot. A slot is drawn from the one side, we can see the two circles. And from the other side, if we view this from the bottom, in this view we will only see that outside edge's hidden detail and the one on the right hidden detail. We will not show the hidden detail for the tangent portion where the arc goes into a flat plane. So we won't show hidden detail over there. Then the center line for a slot. In this view from the side, we show a vertical center line for the center of each of these half circles. From the top, we show the cross center line in the center of each half circle, and we join them in the middle to show that these are actually in line with each other. This is just an example of a slightly more complex component. Big center line for this big circle. Then what we can do is we can make a single bent center line through all of the small circles to show that they are all on the same distance from the center, almost on the same radius, if you will. We can also show a radial center line through them to show the center of the arc to which all of them find the same distance. Center lines are always shown for all cylindrical features. Remember previously I said hidden detail doesn't need to be shown always, so that's why we don't show the hidden detail for there and there. So, precedence of lines. This basically just means which line is more important. If I have one line above another, which one would I actually show? Outside edges are the most important, so if you have an outside edge, you will never erase it to show anything behind it. After that, the important thing is the hidden detail lines, and the least important line is a center line. So it's important to note what's going on over here. We have the center line for that small circle going through there. You'll notice it is in line there. So the center line should be in the middle there. But the hidden detail line for this top edge of the inner cylinder, the big cylinder, that hidden detail line is also in the same place as this small center line. So we then show the hidden detail line instead of showing the center line. The center line is, however, shown on the outside of the component where it protrudes out of the component. At the bottom there, we've got the visible solid outside edge, that corner there, and it also lines up with the center line for the big cylinder. So in this case again, outside edge is more important than center line, so we show the outside edge. Center line is still visible in the background where it protrudes out of the component. This is just an example of what I just said. We've got a half circle that's cut through the whole component. This is a main view. Above it we have a top view. To the right we've got the right hand view. The center line doesn't touch the edges over there, the center line for the big arc, and the reason for that is if we touched over there it would look like a continuation of this outside line. So to avoid the confusion we leave a gap over there and over there. This vertical one can go over the circle's radius because it's not in line with a solid line. Center line for the cylinders, these small cylindrical holes, those center lines are shown as well, and they are shown in all of the views. The same with the center line for that semicircular, cylindrical groove through the top. Center line is shown in the right hand view, although part of the center line is also on the same place as this outside edge. Outside edge is more important, so that's why we show the outside edge, and behind that the center line would just disappear, but it's still visible on the left and the right of the component. Then we go to the projection symbol. Now, projection symbol is a standardized symbol that is used to show someone reading the drawing where they can expect different views to be placed. So, if we now imagine something like a cone, okay, there we have a cone. Now let's go and cut the top off of this cone. Something like that. Okay, so this cone is a cylindrical component because it's symmetric about an axis. So to fully define a cylindrical component, we need two views. That's the one view. And the other view, if I view it from the left hand side, I will see a small circle and a big circle. If I view it from the right hand side, I'll only see a big circle. So the idea of the projection symbol is we take this cone and we then show the reader of the drawing where they can expect different views. For example, a left hand view of this would produce a small circle inside of a bigger circle. Small circle, bigger circle. Now that's basic stuff, but where we place that view is the purpose of the projection symbol. So if we place what we see from the left, if we place it here on the left, so what we see from the left, we place on the left. That means this is the drawing convention or projection convention named third angle projection. Let's consider the other case. Again, we have this cylinder or cone shape from the side. If I place what I see from the left, if I place it on the right, this now means what I see from this side, I can find that picture on that side. So that is first angle projection. The one isn't more right than the other one. It's just basically a standardized way of making these drawings. If you put this symbol in your title block, then the person reading the drawing knows any view to the left of another view would be a left view. If I place this symbol in the title block, the person knows any view on the right of another view would be what that view looks like if I view it from the left hand side. In my personal opinion, third angle is more intuitive, although first angle is what the EGD people were taught at school. One isn't more wrong than the other, it's just two different ways of doing it. So this projection symbol is placed in your title block where it says projection. First angle projection symbol, third angle projection symbol. So now the question, what angle is this example drawn in? So we can see there's a center line through the middle, and that center line tells me that this is a cylindrical component. I've got a big circle, smaller circle, there's a cone, there's a small circle, and there's a very small circle all the way through the middle. Now, if I view this component from the left-hand side, what I would see would be the outside big circle as well as the inside small circle. I would not be able to see these ones if I view it from the left. If I viewed it from the right-hand side, I would see the outside big circle, that smaller circle, the big side of the cone, the small side of the cone, which is the same as that little cylinder on the end, and I would see the hole in the middle. So now the question is, what is this? Is this component seen from the left, or is it that component seen from the right? Now, as I just explained it, this view is that component seen from the right, meaning this is actually a right-hand view placed on the left-hand side. That means it is in first angle projection. The right-hand view is placed on the left-hand side. If I place the right-hand view on the right-hand side, it is called third angle projection. So it's really important to always first start evaluating a drawing by looking at the projection symbol. That tells you where to expect a view on a paper. So I expect the right-hand view of this thing on the right-hand side if it is third angle, and I will expect the right-hand view on the left-hand side if it is first angle. So let's have a look at different examples of orthographic drawing conventions. We'll look at fillets and rounds, the breaking of long objects, intersections and tangencies, as well as cuts. So fillets and rounds in your textbook is on page 28. If you have an L-shaped component with a triangle in the middle, this is more or less what the front, right and top view could look like. But now the question is, what happens if this edge over there is not sharp but it is rounded? So if it's sharp, it's easy to draw, but the question is, if it is rounded, what happens? So that's a bit high. Okay, so this line is now tangent to the big arc at the top and the big arc at the bottom. Now the question is, what would the right-hand view look like? I'm just going to erase this line. Again, I'm drawing in pen over here just to make it easier to see on the camera. The pencils are sometimes a little bit tricky to catch all the little details. So if I have a big radius, the point of contact on that big radius would be somewhere over there and maybe somewhere over there. Now if I view it from the right hand side, that top lines up with that top. But you'll notice now that there's a small height difference over there. If I draw it enlarged, Can you notice there's a visible height difference between the top and where we're touching the radius? So then it means if I want to draw that triangle that touches there, if I want to draw it correctly, I can't draw it all the way to the top because it physically doesn't go all the way to the top. And because with these components everything is rounded, it's almost like it is smoothed. And if we compare it to your manufacturing classes, a component looking like this would typically be a cast component. So then I can't draw these lines all the way straight to the top. So to show that they don't go all the way to the top and they are still nice and tangent and smoothly blending in, I can show the blending by means of these little curls. On this side I've got the horizontal portion, that flat plane there, and it is slightly higher than the point of contact where that blending goes in. So that means the blending must go slightly past and then curl outwards, and then my plane on the inside can come and curl inwards over there. So there's a radius and there's a radius. Just quickly to zoom in over there for you. That is more or less what is happening over there. So if I have a tangent line on a big radius, the way I show that it is still blending smoothly into the big radius would be to let it go slightly over the edge because of the visible height difference, and then rounding outwards to show that it blends in. There, with a tangent line on an arc, there isn't a change in plane over there. It's a nice and smooth transition from the straight to the arc. So I can't make a sharp edge there, it's a nice and smooth one. Now the question is, that was for a big radius where it's obvious that there is a visible height difference. Now the question, what happens if there isn't a visible or obvious height difference? What do we do? So that's basically if we have a shorter or smaller radius. Smaller radius, smaller radius. Okay, let's do the top one first. Because it's a small radius, I can't visibly see that there's a height difference between the point where it touches and the actual top of the component. I know there is a physical height difference, so if I zoomed in like that, I will maybe still see the height difference, but in this view it is too small to show that difference in height. So what we do to show that it's still nicely blending onto that surface, we still do the small radius, but it now touches the top line. Over here we can do a similar thing. There isn't a visible height difference between where it makes contact and this flat plane. It might look something like that. But now there's a problem. I have a vertical flat plane over there and an inclined flat plane over there with a small radius in between them. So a standardized way to show that there is a change in plane, though not sharp, but also not very round. The standard way to do this then is to use your thin pencil and just make a thin line over there. That is the correct way to show a tangency from a flat plane on a small radius. We use this thin line over there. Okay, so in this example, this was the big one. Now with the smaller one, we do the same, but with the line not touching the sides. Same over there. Okay, there's just a summary of the 4 cases. So it's important for you to go and study and understand these and make sure that you'll draw it correctly in a test or exam. So the important thing is that if you draw this wrong, basically what you're doing is you are overriding the manufacturing process. So if I didn't let this big radius one extend past the edges, because I can see the vertical difference, if I didn't do it and I just let it touch the sides, I'm basically changing how this component will be manufactured, and that is not allowed. The person making the drawing cannot change how the part will physically look. So the same applies for other shapes. Again, rounding and tangency. There's a big rounding with something tangent, so we won't show a line. There we've got a big radius with something touching it, but it is rounded where it touches. Let's see if I can zoom in for you. So it is rounded over there. Then we show the rounding by means of this little line. This one is, there isn't a change in plane between this flat piece and the cylinder. It's a nice and smooth transition, gradual transition. So then we don't show a change in plane. With this one, there is a change in plane from this straight portion in the top view to the circle. So for this one, you will show the change in plane with that little line. Good, that brings us to the breaking of long objects. Now sometimes the aspect ratio of components is a bit off to practically fit into a drawing. What I mean by that is, if we take something like a broom, or just the stick of a broomstick. Okay, now it's very hard to actually see the radius and everything going on that end, because to fit it into the page, the diameter needs to be drawn very, very small. So this is not very practical. The cross-section doesn't change from one side to the other, so there's not really a point in us drawing the entire length. We're not showing more information by doing the whole thing. So an easier way to do this would be I'm going to finish that now. If we did a right-hand view of that, it's going to be seriously small. Again, having views that small on a page is probably more dangerous than helpful, because people won't know what's going on there, and then they'll assume, and they'll assume wrong. So the standardized way to break a long object shorter, basically we're taking that part in the middle and We are just drawing it as if it was shorter. Although the dimension, when we place dimensions on this, we'll still use the original dimension. We just draw it in a shorter form. So the standardized way to show that an object is circular is to make this almost like a S shape and then draw these lines on the inside surface. We do the same S shape on the other side. Like that. So this is now the correct way to break a long cylindrical object. The center line will go straight through both sides. This now allows us to make a more appropriately proportioned right-hand view. Which is a lot easier to put a dimension on. That one is so small you can't see what's going on. So that was the way to break a cylindrical object. A non-cylindrical or non-square object you can just break using a wavy line. That is the continuous thin freehand line that we showed in the line alphabet. So this just enables us to a lot more clearly show the dimensions of these holes. This was the solid circular one I just showed you guys. The square one is broken with these zigzag lines, and a hollow circular is done similar to the solid except that we draw the hole on the inside as well. Please go and study those methods. This brings us to intersections and tangencies. So the question now is, practically speaking, how do we draw when objects interact with each other? If you've got a very small diameter circle touching a big one, this small circle won't really hug around the big one enough for you to really be able to see what's going on there. So if you have a small one against the big one, then it is okay to just not bother with the curve. However, as this small diameter increases, it will start to move around this outside edge. So it will move from this point, start to move that direction. So as it moves around the edge, the hugging around will be more and more visible. So as it gets bigger, it starts to hug around this arc, and now from the bottom, the point where it makes contact is now visibly left of the point on the edge of the big cylinder. So it will start to hug around it. For the projection, you can see this picture there. Then we get to a point where they increase up to the point where they are the same size. And in that case, it's actually just drawn as a straight line. So it hugs around to the middle and then back again. So it's important for you to understand this hugging around concept and when to use it and when not to use it. The same applies for cuts. If you have a narrow groove into a component, from this view I won't really be able to see the vertical drop because this hole is now traveling down this arc. As the hole gets bigger, however, it moves further down the arc and then the vertical difference starts to become visible. So if it's a narrow groove, we don't mind if you just draw a straight line. As the groove gets wider, you'll have to start to draw what it would actually look like. The same applies to a circle. And at the end of these slides we've got 2 practice problems which you are welcome to go try out. I think it's a good idea if we just quickly do practice problem 1 together. So something to note, it's a big cylinder and it is slightly lower than this right hand side. We can see the height difference by this construction over there. Okay, let's quickly draw that one. So we must now make an orthographic drawing of that component. I'm going to start with the main view. The main view has more or less that kind of shape. Okay, let's do the top view. Remember that these views need to be in line with each other. I'm just going to bring the question back again. So in this question you'll notice that these vertical feet on the right hand side are slightly narrower than the diameter of my big cylinder. So it means the cylinder in my top view will be slightly lower than those feet. Okay, and then on this right hand view, should go a bit further down. Okay, let's quickly finish these fancy roundings. So in my top view, you can notice I've got a rounding over there. The same on the other side. Now, that is the edge of the cylinder. The point of contact is left of that, meaning this line will be slightly left of the edge of the cylinder. Then, to show that it is blending in, like a nice and rounding going on there, I do the little rounding. This one, where it meets this surface, it is rounded as well. Something like that. To show that this is a change in plane from the straight to the cylinder, remember it's a cylinder and a straight one with a small radius in between the two. So a small radius will mean I need to just make that line to show the change in plane. That's a thin line that doesn't touch the sides to show that I'm not tangent to the big circle. I am at an angle, but it is a blended or radiused angle. So it's smooth but not too smooth and not too sharp. That's what that little line does. On this side there we've got a radius, there we've got a radius, 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 sharp corner, sharp corner, big cylinder. But I'll still see the big cylinder in the background there. In the top, radius, radius, straight, straight. There is a hole through the middle, something like that. Okay, next what I can add is I can add my center lines. Because this groove, that arc over there, is in line with my big circle, I'm using the same center line, and doing that shows that these two are on the same level. Center line for my big cylinder, center line for this half cylinder cut up there. Remember, that line shouldn't be there. Okay, next I need to add the hidden detail. Hidden detail of this cut out in this view would be over there. The hidden detail for the hole through the middle must only be shown in one other view. So I only show hidden detail of a feature in one other view. So I can show the hidden detail for this cylinder in this view, or I can show it in that view. No problem. I'm going to place it in this view because this will not be behind other stuff in that one. It's nicely on its own. Something like that. Hidden detail for this flat plane over here. Okay, the center line for the cylinder still needs to be shown in my right hand view, so that center line for the cylinder and the center line for this little half circle lie on the same place, so that's why I show them both. And that is how this one was done. Okay, thank you.